So in this video we're going to look at limiting reactant calculations, and these are similar to reacting mass calculations, but there's a couple of extra steps with these. And these stem from reactions where you're given the information of both of your reactants, or three, even if there's three reactants, you would be given the mass of each of those reactants. And why we need to do this, and why we need to proceed with the calculations this way, is because in a chemical reaction we rarely mix the just right proportion of the reactants when we carry out a reaction. Often one reactant is more expensive than the other, so we tend to use less of the more expensive one and use the other reactant that is cheaper in excess, so that all of our expensive reactant is used up and none is left over at the end of the reaction, but the other reactant that we have used in excess will be. Okay, so just to introduce you to these terms, although you would have met them at GCSE when you did this type of calculation, the limiting reactant in a reaction is the reactant that limits the amount of product that can be formed. So essentially it is the amount that when you've worked out the number of moles and when you've worked out the ratio of your reactants, it's the one that you have less of. Okay, now you may have added in a higher mass of it, but in terms of moles and in terms of the ratio, it's the one that you have less of, and it stops the reaction from going any further, and the reaction will stop when all of the limiting reactant is consumed. The excess reactant, or there could be more than one of them, if you have, say, three reactants in a reaction, it's the one where we've added in excess, we've added more than we need of, essentially, and there'll be a bit of it left over when the limiting reactant is completely consumed, and it remains, the reaction can't go any further because it has no other reactant to react with when the limiting reactant is used up. So when we were in class, we looked at a wee example of making packed lunches, and you can see there's one example that's been given to you here. So you can think of making a packed lunch as your reaction, with your packed lunch as the product as such. So the reactants of your packed lunch are one sandwich, two cookies and one orange, and then your packed lunch is your product. Okay, so you can see here in then diagram B, we start with 11 sandwiches, 16 cookies and 10 oranges. That's the amount of reactant that I start with. So if we try to make up packed lunches, you can see there on the right hand side, we'll get 8 packed lunches. And that's because of our cookies. Our cookies are our limiting reactant in this case. So if we need 2 cookies for every 1 packed lunch, then we can only make 8 packed lunches because we've only got 16 cookies, so 16 divided by 2 is 8 packed lunches. So what that means then is we'll be left with some leftover sandwiches because we started with 11, so we'll have 3 leftover sandwiches. We started with 10 oranges, so we'll have 2 leftover oranges because we only made 8 packed lunches. So in this case, even though we started with more cookies than sandwiches and oranges, because of the ratio in which they react together, the cookies are the limiting reactant. Because once there's no cookies left, we can't make any more packed lunches. And so there will be excess sandwiches and oranges. So sandwiches and oranges are our excess. The cookies are our limiting reactant. So this is an example where you can see you need to work out this in terms of the ratio of the reactants that you need. So even though we had more cookies to start with, we had 16 versus 11 and 10 sandwiches and oranges. But because we need 2 for each product, our packed lunch, then it is actually ending up being our limiting reactant. So we need to take that into account when we do these calculations. So let's look over on the next page at our steps of these calculations before we look at some worked examples. So the steps are very similar to the reacting mass calculations, but as I said, there's a couple of extra steps. So the first thing is to make sure you write a balanced symbol equation for the reaction. It must be balanced because we really need to know our ratios in which our reactants react together in order to correctly identify our limiting reactant. Number 2 then, calculate the number of moles you have of each of the reactants. So how you'll identify this type of question is they'll give you the mass or the volume or whatever of more than one of your reactants. So you'll know from that you need to work out how many moles do I have of each and which is my limiting reactant. You'll then need to divide through by your stoichiometry, in other words, your balancing number ratio. And that's a bit like in our packed lunch example, taking into account the 2 cookies, the fact that we needed 2 cookies per product. We need to take that into account with our real reactions as well. So that's why step number 3 is there. And I'd put a star at it or highlight that, because that's the one that most people, or is most commonly forgotten about. And it can lead to you identifying the wrong limiting reactant, which we'll see in one of these examples down below. Determine which is the limiting reactant. So that's after you've divided by the stoichiometry or the balancing number. It'll be the lowest value of the moles after you have divided by the balancing number, not before, but after. And this is the value of moles that you use when you're calculating the number of moles of your product. So in this case, we'll use these steps now to go through worked examples 1 and 2. So if we look at worked example 1, it asks what mass of magnesium chloride. So just as we did the other day, let's underline what they're asking us for and the information that they give us. So it says what mass of magnesium chloride, so we can put a question mark there, is obtained when 25 grams of magnesium, so that's an information I've been given, I'll underline that in a different colour, is combusted in 90 grams of chlorine gas. That just means it reacts with or is burnt in 90 grams of chlorine gas. So here I would be saying in my head, right, they've given me 2 values, this must be a limiting reactant calculation. So our first step is to write a balance symbol equation. We must do that and balance it carefully before we proceed. So we are reacting magnesium with chlorine. We need to remember that chlorine is diatomic to produce magnesium chloride. So let's have a think about what our formula of magnesium chloride is going to be. Magnesium is in group 2 of the periodic table, so has a valency of 2. Chlorine is in group 7, so has a valency of 1. Remember, it's not diatomic anymore when it is part of a compound. We swap and drop that and we get MgCl2. So you need to work out your formula accurately. We need to check that this is balanced, but in this case it actually is already balanced, so we don't need to go any further at this stage. Okay, then just as we did before on Monday with our reacting mass calculations, what I want us to do is write the information we've been given underneath the equation. So we're told that we have 25 grams of magnesium, and that's in the correct unit, so I don't need to do anything with that. We've got 90 grams of chlorine, again in the correct unit of grams, so we don't need to do anything with that. And the thing I've been asked to work out is my mass of magnesium chloride. So I'll put question mark mass here. Okay, so you might look at that question and say, well, clearly we've got less magnesium than we do chlorine. That's by mass. We need to work out which we have less of by the number of moles, because that's where we can determine the ratio in which our reactants react together and our products are formed. We're going to need the RFM of all of these things where we've written any bit of information. So let's write that down now so that we're ready to just do our equations when we need to. So you'll need your periodic table out again today. So RFM of magnesium, it's just 1 atom of magnesium, so that's going to be 24. For chlorine, it's 2 atoms of chlorine, so that's going to be 2 times 35.5, which is 71. And then magnesium chloride is going to be 24 plus 2 times 35.5, and that comes out as 95. So what we need to do now at this point is we need to work out our number of moles of magnesium and of chlorine. So to do that, we're just using the same old equation, N equals mass over RFM, or whatever format you do that in, moles equals mass over molar mass. Either's fine. Your mass is 25 for magnesium and your RFM is 24. So I'd encourage you to do this in your calculator along with me. And that comes out as 1.042 Those decimal places may continue. I've rounded it off just to, in terms of keeping this tidy and keeping this fitting in. But again, as I said before, try not to round off your answers too early. What you can do, I'd really encourage you to use the store button in your calculator. If you're not sure about that, ask me when you're doing some practice questions. But if you store, you'll see, I think it's like shift, store, and then like A, B, C, D, E, F, there should be in your calculator. And it means you can store that number as accurate and then use it later on once we've identified the limiting reactant. So I would encourage you to make use of that. If you're not sure how to do that, then let me know and I will help you later on when we're trying some questions. Or you can put it back in as a fraction when you're using it later. Okay. Now, what I would encourage you to do is at this point, divide by your stoichiometric ratio. In other words, your balancing number ratio. Okay. In this example, I do know it won't make much of a difference, but it's important to do it to get yourself in that mindset of doing that extra step. So what is our balancing number in this case? Just 1, okay? So I know that won't make a difference, but if you could just write that in at the bottom, just to remind yourself to do that in every one of these questions. So we're just dividing by 1, we're dividing by the ratio, our balancing number ratio of that reactant, okay? So let's then look at chlorine and do the same thing to work out how many moles we have of it. N equals mass over RFM. That's going to be 90 over 71. If you put that into your calculator, it should work out as roughly 1.268 moles. Again, I've rounded that off a bit, but again, use that accurately if you are to use that later on in the calculation. Okay, what we want to do, just to remind ourselves, is that step number 3, divide by the balancing number ratio, which again is 1. So that's going to be 1.268 moles. Okay, so for this, dividing by the balancing number ratio hasn't made a difference, but it's important that we think through that for each of these calculations. So which do you think is your limiting reactant? Which do we have less of in terms of number of moles? Yeah, the magnesium, okay. And it's always the smaller number of moles at this stage after you've divided by your balancing number, okay? So I would put a box around that and even write LR beside that. That's your limiting reactant. And that's the number of moles that we bring over. Because once those 1.042 moles of magnesium is used up, yes, there will be excess of chlorine, but it will not be able to react anymore because there'll be no more magnesium left. So what we would do is bring this over to our magnesium chloride, and you need to be careful about your ratio here, because what you need to remember is that, and again, it won't make a difference here, but it will in later examples, you've actually already done the first step of the ratio. You know, when we were moving ratios over before, we would have divided by the first number and times by the second number. Here you've actually already done the divide by 1 stage. So really we're just timesing by 1. And again, I know that doesn't make a difference here, but it will in the next example. So if you're not sure what we're talking about here, we'll see this in the next example. But just remember that you've already divided by your first balancing number. So you really just need to multiply by the balancing number that you're going to. So that means in theory, we'll produce 1.042 moles of our magnesium chloride, in theory, okay? And then all I'm doing, same as yesterday, or same as Monday, doing mass equals N times RFM, putting in 1.042 times by your RFM, which we already worked out as 95. And again, try and use the full number of that 1.042. So either you've maybe stored it from this part of the calculation, or put in again 25 divided by 24 from over here, and then times by 95, just to keep your answer as accurate as possible. So I got that coming out then to round off to 3 significant figures, or 1 decimal place, as 99.0 grams. Let's do one more example together, and this example is one where we will need to be a wee bit more careful about our ratio, so it'll be good to look at a reaction like that, okay, or an example like that. So it's a similar type of reaction, but we'll have different values here. Here we're asked what mass of aluminium chloride, so that's our question mark, is formed from the reaction of 25 grams of aluminium with 90 grams of chlorine. Okay. So again, you can identify that this is a limiting reactant type in that you've been given the information for 2 of your reactants. Okay, so first things first, write your balance symbol equation. I would encourage you to spread it out across the page so that you have enough room to work underneath for each of these reactants and products. So aluminium is just Al, chlorine is Cl2. Aluminium chloride, well, we need to work out its formula. It's going to be Al with a valency of 3. With chlorine with a valency of 1. When we swap and drop that, we get AlCl3. Okay, so we do need to balance this one. So the only thing that's not balanced at the minute is our chlorine. And you can see that if we put a 2 in front of our Cl2, that's not going to fix it. We're actually going to need to put a 3 in front of our chlorine to then put a 2 in front of our aluminium chloride, and that will get us 6 chlorines on each side. Okay, now if you're not sure about jumping straight to that step, that's okay. You can put a 2 in front of here, your chlorine, but then you'd figure out that you would need more on this side, and that would end up putting your 2 here and changing that to 3 in the end. That was just kind of skipping out that step. And you'll also then need to balance your aluminiums by putting a 2 in front of your Al. Okay, so balancing the equation is so important in these types of calculations. So just as we did before, and you can go ahead and do this, is to write the information you've been given underneath the equation. So put a question mark mass underneath your aluminium chloride. You've got 25 grams of aluminium and you've got 90 grams of chlorine. So let's work out our RFM of all of these things. Just a reminder from Monday, you do not include the balancing number when you're working out the RFM. The RFM is literally the mass of one formula of that substance. The balancing number ratio, that's only for this particular equation, that these reactants react together in the ratio 2 to 3. So we don't take the balancing number into account with our RFM. Otherwise, you end up doing that step twice. We'll take that into account with the ratio. So the RFM of aluminium, it's just 1 atom of aluminium. So it's going to be 27. RFM of chlorine, which we saw in the previous example, is 71. That's just 2 times your 35.5. Again, ignoring the 3 for now. And then the RFM of aluminium chloride, that's going to be 27 plus 3 times 35.5. And that should be 133.5. Okay. So now we've got all our information and we're ready to go with our calculation. So what we need to do at this point is work out the number of moles of each of our reactants and then think about the ratio of each of them. So first of all, of aluminium, N equals mass over RFM. It's going to be 25 over 27. And that comes out as roughly 0.9259 moles. Again, if we end up using that number later, we'll use the more accurate version of it. What do I need to do at this stage? Say again? Good, divide it by 2. So at this point, we divide the number of moles of aluminium by 2. Why? Well, because we've got a balancing number of 2 here. So we divide by 2. And again, keeping your number accurate. So once you've got this answer of 0.9259 in your calculator, rather than clear it and type it again, just type in divide by 2 equals, that keeps your number nice and accurate. And that should come out as 0.46296. And that again probably continues, but we'll round it off to there for now, and then we'll use it as accurate later if we need to use that one. Let's do the same for chlorine. So we're doing N equals mass over RFM. Our mass is 90. Our RFM is 71. That should come out as 1.2676 moles. And again, that might continue. What do I do at this stage? Good, divide by 3, because I need 3 moles of chlorine for every 2 moles of aluminium. So we divide by 3, and that gives us 0.4225 moles. Again, I've probably rounded that off a wee bit, but we can use the accurate number if we're using that number. So what you do at this stage is you look at these number of moles after you've divided by the balancing number ratio and ask yourself which is the limiting reactant and which is it in this case. Good, it's the chlorine. So can you see with this example why it's so important to take in your ratio? Because if we'd looked at it at this stage with our 0.9259 and our 1.2676, we would have said that aluminium was the limiting reactant. Because yes, we have more moles of chlorine, but because of our ratio of 2 to 3, overall, in terms of the ratio of what we need, we have less of chlorine. So it's this that we take over. So I would put a square around that and say, well, that's my limiting reactant, okay? And sometimes the questions are just identify the limiting reactant, but you still need to go through this process to recognise and identify that. But here's where you need to be careful with our ratio. So on Monday, when we were doing these reacting mass calculations, we would have said the ratio of chlorine to aluminium chloride is 3 to 2. And what that would mean is we would divide by 3 and times by 2. But can you see how we've already done the divide by 3 stage here? So what am I going to do when I bring this number of moles over? Just multiply by 2. So at this stage, when you've already divided by your balancing number of your reactant, you're really just multiplying by the balancing number in front of your desired product, the one that you're working out the mass of. Okay, so think about that again. The ratio is 3 to 2 overall, but you've already done the divide by 3 stage. If you need to make yourself a wee note of that, then please do. We're only multiplying by 2 because we've already done the divide by 3 stage. We've already divided by the number in front of our reactant. So this time with these calculations, it'll just be times by whatever's in front of your product. Okay, again, try and keep that number accurate. So if you've rounded that off here, maybe put in your 90 divided by 71 again, or store the number, and then just type in times by 2, and that should work out that your number of moles of aluminium chloride, if you've kept it accurate, should be 0.84507 moles. Okay. So you can see that would have been different had we rounded off at this stage. So try to refrain from rounding off too early. And then it's just a case of doing mass equals N times RFM. So that is your 0.84507 times by 133.5. And that should come out as, again, if we round it off to 1 decimal place, 112.8 grams. And make sure to always put your units at the end of your calculation. We're working out the mass. So remember, if we've used these equations as they are, then the mass will come out in grams. So if you now have a go at exercise 10, these are your limiting reactant calculations. So on page 36, and they also continue on page 37 as well. So if you want to complete questions page 36 and 37, there's 6 in total. So just make sure you follow through each of your steps really carefully. If you are if you're not given an equation, you need to write a balance symbol equation, and you may want to use your general equation sheet that I gave out to help you write those to make sure you know what your products are. So for example, question 2, you've got a metal hydroxide reacting with acid. So you need to know that that produces a salt and water. Next one is ammonia reacting with sulfuric acid. Well, although there you're told the product, so you just need to convert that to a balance symbol equation. So where you're not given an equation, just be careful to write that accurately. On the next slide then, I will show you the answers for this exercise, and you can even write the final answers in beside the question, so that you know when you're doing these if you are getting them right or not. And if you don't get the same final answer, go back and see if you can identify where you've gone wrong. And if you can't work out where you've gone wrong, then send me a photo of your working out, and I'll try and help you and point you in the right direction. But go through your worked examples, make sure you're following through each step really, really carefully, and doing the same thing each time to make sure you don't miss out a step. So here are the answers to the exercise questions 1 to 6. So again, you can write these in beside the questions so that you can check your answers as you go along. So if you pause the video and write in the answers so that you know how you're getting on.